All right. So today we're going to talk about a general technique for designing streaming algorithms. It's called linear sketching. Okay. And this is something that is useful for designing streaming algorithms, for designing sketching algorithms that operate in data streams, as well as other sketching applications like distributed applications where each, say, machine wants to sketch its data and then send something over the wire to some central server that's going to compute on the aggregate of all the sketches. We'll see some of that later when we talk about graph sketching. But what's the idea behind linear sketching? So the idea is you represent data as a high dimensional vector, x, and is very large, right? And I'll give examples. I'll show that some of the stuff we've been talking about already can fit in this model. You'll pick some matrix, pi, which is an m by n matrix, where m is much less than n. So pi looks like a short, wide matrix. And you'll store in memory is pi x, right? So x is this very huge object. You don't want to spend n memory storing x, so instead you store pi x, and that's only a size m object. And if m is very small, then you've saved a lot. You have to worry that, well, pi, yes, y is small, but pi is not small. Pi has more than n numbers. It has mn numbers. So if I have to store pi, isn't my algorithm doing very poorly in terms of memory? But as we'll see, in a lot of linear sketching, you try to design a pi such that even though pi is a big matrix, it can be represented very succinctly. So for example, pi might be deterministic, and you never have to write pi explicitly in memory. You just have to design an algorithm which, given I and j, can compute pi ij efficiently without actually having to ever write down the whole thing. Or maybe pi is random, but it's generated using a 2i's independent hash function or something like that, so that you don't you just need to remember the seed that defines pi. You don't need to actually ever write pi down. And this is in streaming. In streaming, this is related to something called the turnstile model. What's the turnstile model? In the turnstile model, basically, you must maintain this vector x, which starts as the 0 vector, subject to updates of the following form. Update I comma delta makes the change xi gets incremented by delta, where delta, say, is some real number. So, when we talked about, for example, distinct elements, or even quantiles on a bounded universe, we always have delta. We always have delta just being 1, right? And x was a histogram. So for example, in distinct elements, let's say, you see a stream that looks like 1, 1, 4, 1, 5, 2, 1. Of course, the number of distinct elements here is 1, 2, 3, 4. These are distinct elements. But this, you can view this stream as being represented by a 5-dimensional histogram, where the ith entry is how many times you saw I in the stream. So you saw 1 3 times, you saw 2 once, you saw 3 not at all, you saw 4 once, you saw 5 once, right? Does that make sense? So I'm just saying these is 1, 2, the number of times you saw I is xi. And then you have a query that you want to answer, and the query is some query about this histogram. So, for the distinct elements problem, the query you're making is how many entries of the histogram are non-zero. Okay, in quantiles, if you're working with quantiles over a bounded universe, then you imagine that X is a U-dimensional vector where U is the size of the universe. And again, X is so it's a histogram. And then you're basically asking, if I'm asking for, let's say, rank, what's the rank of I? I'm saying sum up all the entries in this histogram leading up, up to and including I, from 1 to I. That's the answer to a rank query, right? So, all the problems we've been studying so far can be modeled by this, turnstile model, with delta always being 1, because when you see an item, you just add the 1 to the corresponding entry in the histogram. Now, in a turnstile model, there are kind of 3, you could say, special cases or submodels. So there's the insertion only model. That's where delta is equal to +1, always. And that's what we've been looking at so far. We've studied so far. Oops. There's also what's called the strict turnstile model. Delta can be whatever. It can even be negative. But we're promised that no xi can ever be negative. Okay, and where does that show up? You can imagine you're doing some kind of graph sketching problem or streaming problem. We're going to see that in a later lecture. So the idea is this x, this high dimensional vector. Imagine you have a graph on v vertices. So I'm going to imagine my x is actually a v choose 2. Let's say it's an undirected graph. It's a v choose 2 dimensional vector, where the ij entry of the vector of x is basically 1 if that edge is in the graph, and it's 0 if it's not in the graph. Or if it's a multi-graph, xij is like how many copies, what's the edge multiplicity of ij in the multi-graph. And you can imagine my stream is just monitoring activity on social media. So I and J become friends on Facebook. So that's adding delta equals +1. I added an edge between I and J. So xij got incremented by 1. And then all of a sudden, later they one of them unfriends the other. They're not friends anymore. So I deleted an edge. Okay. But you can't delete an edge more times than you inserted it. So you're promised that xi will never be negative, right? And I mean, if it's not a multi-graph, it's of a simple graph, then you're always even promised that all the xi's are either 0 or 1. But even in a multi-graph, yes, in a multi-graph, the xi's could become large positive numbers, but they're never going to become negative. It doesn't make sense to talk about negative edges. Or just in general with strict turnstile, you can think of it as representing insertions and deletions. So you're maintaining a set of items. You can insert items, you can delete items, but you're never going to delete an item if that item isn't already in your set. And then there's the most general turnstile model, which basically says anything goes. So things can go negative. And why might you ever want to consider a problem in that model? Let's say you want to do something like change detection. Okay, so there was a stream yesterday over some universe. The items come from some universe, and then there's a stream today where the items are coming from the same universe. Like I'm seeing search terms on Google. Okay, and I'd like to answer queries about what changed a lot from day to day. Like what are the words that were very popular search terms today but were not popular search terms yesterday? Okay. So there, a natural thing to do is I can treat every update yesterday as a positive +1 update, all the updates today as a -1 update, and then what's xi at the end of both days? Xi is the difference between the number of searches yesterday for that word versus today, and then I want to find the words that have big differences, right? So that's some kind of query on this difference of histograms, but I can model that as a general turnstile problem. Okay. And where does linear sketching fit into this? Notice that saying that I have the update xi gets to xi plus delta. This is the update I delta in the turnstile model. That's the same thing as saying x gets x plus delta times ei, where this is the ith standard basis vector. And that means that, remember that y is equal to pi x, right? So that means that y becomes y plus pi times delta ei, which is just y plus delta times pi I, where you imagine that the pi i's are the columns of pi. So this column is pi 1, this column is pi 2, etc. So what this says is, you can in the turnstile streaming model, if you're doing linear sketching, it's very easy to maintain your sketch after an update. If someone makes an update to the ith entry of your histogram up to x, that just corresponds to adding some multiple of the ith column of pi to your sketch. Okay. Good. And I should mention, actually, there's been work. So for a while, for a while, people were noticing that in the turnstile model, all the papers that researchers were writing were always, the algorithms at the end of the day were linear sketches. Okay. And it wasn't clear whether that was just a coincidence, but in fact, there was a paper in 2014 by Yi Li, Hui Wen, and David Woodruff that said that basically linear sketching is universal for turnstile streaming. What does that mean? What do I mean by that? So I'm not going to write down the formal theorem statement because we're not really going to talk about it a lot today. I'll just give you the gist of it. Basically what their theorem said is, say you have a problem and say you have an algorithm that solves that problem efficiently in the turnstile streaming model. It uses S words of memory. You have no idea how that algorithm works. You just know that there is an algorithm. Then their theorem is just the fact that that algorithm exists implies that there exists a linear sketching algorithm for the same problem. Okay, so you can represent the algorithm as maintaining pi x for some pi, such that pi has something like s rows or O of s rows, which, the number of rows, remember, you're maintaining pi x in memory, so the number of rows basically is your memory, other than the memory required to store pi. There were some caveats in their theorem, like the pi that they construct is not necessarily small to represent. So it might not necessarily give you a low memory algorithm. But it's just like a proof of concept that's maybe a hint why people haven't, it's a hint that explains why linear sketching has been showing up so much, that basically even, it just is essentially the only thing you can do in the turnstile streaming model. That being said, there were some assumptions in their paper, like, you have to assume that the original algorithm works on arbitrarily long streams, or at least, doubly exponentially long streams in the universe size or something like that. And if that's true, then that implies that there's a linear sketching algorithm. So, if you're trying to solve a streaming problem, a turnstile streaming problem, and you're promised that the stream isn't super duper long, like, it's only poly-n in length, then their theorem does not apply. In fact, there's another paper, this is going to be in the lecture notes, that shows that in such cases, when you have shorter streams, not even that short, but just shorter, like poly-n in length, there are algorithms that probably do better than any linear sketch could do. Okay. So this is a very active area. I mean, the most recent of these papers, I think, came out earlier this year. So if you're looking at final project ideas, you can take a look at some of those papers. Again, I'll put the references in the notes. Okay, so let's try to make this concrete by actually designing some linear sketching algorithms, and we're going to do it today. And we're going to be on the topic of linear sketching for a while because it's a very I guess common technique that's just applied all over the place. Um, so a lot of the problems that we're going to study from now on turns out that the best known way to solve it is using linear sketching. So today we're going to apply linear sketching to the frequent items problem, also known as heavy hitters.
Jelani, are you writing something?
Oh, yes, I am. And I see that it's not coming out. Let me actually make sure.
It's coming out now.
Yeah, but it's not a good sign that it's taking so long. Sometimes my iPad just likes to connect to, again, the wrong Wi-Fi network. So now it's good. Okay, so now it should be better. Okay, so what is this problem? So this problem, oops. So this problem here is some notion of approximate top K. So, forget about, so remember I said there's insertion only, there's strict turnstile, there's general turnstile. So what we've been talking about so far in this course, the examples have, I think, all been insertion only, right? Where delta is always +1. So let's just think about that for a second. And, you're seeing a bunch of items in a stream coming from some bounded universe. There could be repetitions. And what I'd like to know is just, what are the top K items by frequency? You could imagine, again, I'm monitoring a search engine query stream. What are the top 100 words that people have been searching for over the last hour? Okay. Now, we talked about, so you can ask, what is the complexity of this problem? Unfortunately, if you want to do exact top K, this is hard even for K being 1, meaning you need omega n memory. And we saw a proof of this, right? The proof of this was, we talked about the communication complexity of a problem called multi-party set disjointness, right? So why is it hard? There's a reduction from multi-party set disjointness. So remember there, Alice has some X, which is in, actually there's going to be sets. Alice has some set S, which is a subset of 1 to n. Bob has T, which is a subset of 1 to n. They're promised that either S intersect T is empty or it's not empty, okay? I mean, it's not a promise. One of those definitely has to be true. They just have to decide which case they're in. Okay. And it's known that this needs omega n communication. Okay, omega bits of communication. So, which is essentially, there's a difference between bits and words, but omega n, you need, if you want to just store the entire histogram, that's only O of n words of memory. So other than the difference between bits and words, this is basically saying that there's nothing that much better than the trivial solution of storing the whole histogram. And, if you could solve top K, where K is 1, show me the item is the largest frequency, then you could solve disjointness, right? Because, well, let's say that your algorithm not only identifies the item, but gives you some approximation to its frequency. Alice can run the top K algorithm on her input S, feed the memory contents to Bob. Bob runs it on his input. Now, the top frequency will either be 2 if they're not disjoint, if they intersect. Some item in the intersection, has some item in the intersection has frequency 2. Otherwise, the top frequency is 1. They don't intersect. And if you can distinguish these two, then, and if you can actually tell me which item is in the intersection, then you've solved disjointness, right? So this problem is hard. And you might worry and say, okay, well, Jelana, this is saying that if you can not only tell me who the top item is, but also tell me his approximate frequency, that's hard. But what if I just want to ID the item and I don't necessarily want to know its frequency? Then remember, we talked about the multi-party set disjointness, where it's not just 2 players, but it's little t players. We showed that even that version is hard. So you can imagine that the first 2 players, basically just try to identify, they just use the streaming algorithm to identify the name of the top 1 item. And then the second player, Bob, once he knows the name of the item, he'll just, well, I guess then it's, then it's over. Just knowing that there's an item in the intersection is it, right? So once Bob thinks he found an item in the, once Bob finds out the name of the item that's the top 1 item, he doesn't necessarily know whether it appeared once or twice, because if everyone appeared once, then the top 1 item only appeared once, right? So just knowing the name doesn't tell you whether it appeared once or twice. But if he knows the name, he can then just send the name to Charlie, who's the 3rd player, and Charlie can check whether or not that item is in his set too. And if so, then you know that indeed you're in the case where that item is in all the sets. So these sets are not disjoint. So you solve disjointness. So if you want to solve the exact top K problem, forget it in low memory. It's going to take you a lot of memory. So we settle for some approximate notion of top K. And right now what I'll talk about is something called the L1 heavy hitters problem. So there's given some parameter K. Which is a positive integer. It's like the top K, it's that same K. And I'll say item I is, I'll call it K heavy, or I'll also call it, sometimes I'll call it K frequent. If xi is bigger than 1 over K times the sum over all J, goes from 1 to N. Xj. Of course, this is just the L1 norm. That's why it's called L1 heavy hitters. How many items can possibly be this heavy, at less than K, right? Because you're saying that this item's contribution to the L1 norm is more than a 1 over K fraction of the total mass. How many items can be more than a 1 over K fraction? Less than K. So the total number of heavy hitters is less than K. It's at most K minus 1. Right? So the goal is, let's say, when someone says query, output a list L, which is a subset of the universe, such that 1, if I is K frequent, meaning it's a heavy hitter, that implies that it should be in the list. And then 2, okay, so let's say that the goal for item 1 is just let's say that my only goal was that my only requirement is that L satisfies item 1 when someone says query. Then why would that be a trivial problem? Just so we're all on the same page here.
You just return all of L or all of N?
Yeah, I can just say, oh, the whole universe. So to make it a little more interesting, I'll say that L has to have bounded size. So I want to have a list of size, say at most 2K or 3K, that's guaranteed to contain all the K frequent elements. And of course, I know that the true L doesn't need to have size more than K minus 1 because they're at most K minus 1 frequent items. So I'm willing to allow an L that's slightly bigger just by a constant factor, but not that much bigger. So
Is there a
that's the L.
reason?
Yeah.
Is there a reason to restrict our attention to when the parameter k is an integer?
No, you could, yeah. So yeah, you can. You don't have to. I mean, yeah. I mean, you can imagine k is not an integer, but I guess this thing I'll say. Okay, you know what? So it's
What?
not going to really affect much because all our complexities are going to be like, depending on k or k squared or something like that. So whatever k is, you can just round it up to the nearest integer, right? And
Sure.
you'll solve the original version where it wasn't an integer even better because you have a better error parameter.
Wait, but why would it even matter if k is not? Because like k is just looking at frequencies, right? Which are all integers anyway, right?
No, but I guess I think what he was asking was, suppose I just want to know, find me everyone who's at least, 2/5 of at least 40% of the total weight of the stream, right? So what's k now? K is basically 5/2, right? Because you're at least a 1/k fraction. So that's not an integer.
Isn't that not what we're doing there? I thought we were finding like the top, like the 10. If k is 10, then we're finding the 10 elements that appear the most.
Well, that's yeah. So what you're saying is the actual top k problem, right? That's this. Yes, the actual top k problem is find me the top k items.
Okay.
Unfortunately, that's not a solvable problem in low memory because there's a reduction from set disjointness. Okay, so since we can't solve that problem, we're settling for something that's, some kind of approximation of that problem, right? Notice that if you are more than a 1/k fraction of the L1 norm, then you definitely are in the top k. So
Yep.
if you're a heavy hitter, if you're an L1 heavy hitter, you are in the top k. But if you're in the top k, you're not necessarily a heavy hitter, right? So for example, let's say that I have a million indices that appear once, and then one item that appears twice. That one item that appears twice, it is in the top k for k equals 1, right? But it's not a k heavy hitter for k equals 1, right? Or it's not a k heavy hitter for any constant k. I mean, it's a k heavy hitter for k being a million. You're only a millionth of the, or maybe 500,000th, 1/500,000th of the stream.
Yeah.
And that's unfortunately that's just out of necessity that we had to kind of weaken the definition of what it means to be frequent just to get a problem that is solvable.
And in that case, it would work the same for non-integer fractions.
Yeah, so I guess my comment is, I mean, I usually think of k as being somewhat large, right? So
No,
k
Sure, yeah.
is at least, let's say, 2.
Yeah, that doesn't really matter.
So whatever your k is, just round it up to the nearest integer. Okay. I mean, you will find this problem described in the literature as, the epsilon heavy hitters problem, where, xi is bigger than epsilon times the L1 norm. And then, people just think about epsilon being whatever it is. It doesn't necessarily have to be an integer. For me, I'm just thinking of k as being whatever epsilon. And, I'm just thinking, what if the epsilon you're interested in was not an integer, just round it so that k is an integer. So that whatever epsilon is an integer. That doesn't really change epsilon by much.
Yeah.
Okay, so a related problem is what I'll call the L1 point query problem. So when someone says query, you have to return xi plus or minus, you're allowed an error term of at most 1/k times the L1 norm. Okay. So you have to return a value in the interval from xi minus 1/k times the L1 norm to xi plus 1/k times the L1 norm. Okay. And why did I say they're related? So claim, if an algorithm A solves, let's call it the 3k L1 point query problem. So here I mean, it's solving L1 point query where the k parameter is actually 3k. So suppose it solves this with space S and failure probability at most, let's say delta over n, where n is the universe size. Then there exists an A prime, an algorithm A prime, solving the K L1 heavy hitters problem with, let's say, space S plus O of K and failure probability at most delta. So what's the proof? So I'm supposing that I have this algorithm A. A prime is going to use A as a black box, right? So, feed A prime. A prime will feed all updates into A, and then when you query A prime, what do? So you say for, let's say, I equals 1 to n, xi tilde gets a dot query I. So I just basically query everyone in the universe, okay, and I ask A for an approximation to xi, and then I let L be the 3k values of I with the largest point query values in magnitude.
Wait, what's the point query problem?
This is the point query problem.
Oh.
Okay, so point query it's a streaming problem, a turnstile streaming problem. X is getting updated in the stream, and then at query time, there are n different queries that the person might want to query. If they say query I, then what they want is an approximation to xi. You should return xi up to some additive error, and that additive error should be at most 1 over k times the L1 norm, okay, in magnitude. And the claim is that if you can solve point query, you can solve heavy hitters, right? I mean, it sounds kind of sensible, right? Heavy hitter says, return to me everyone who's very large. Return to me the largest people. That's what it wants to solve. Point query is, I want a data structure such that given any I, you can tell me xi. You can tell me how large it is. So now how am I going to use that data structure to solve heavy hitters? I'm just going to point query everyone. So now I know everyone's size, and then I'll just return the people that look the largest.
It's X is the vector of the frequencies of all the elements I in the universe.
X is, so in turnstile streaming, there's always this underlying vector X, which is getting updated, right? People are allowed to add delta to xi for some I and some delta. So in the stream just looks like a bunch of updates. Update I1 delta 1, update I2 delta 2. You're just adding various things to various entries in X. Alex, did you have a question?
Yeah, what's special and why is there a 3? Where does that come in?
Yeah, so we'll see. We'll prove this.
Oh, okay.
We'll see why the 3 comes in. Any other questions? Okay. That's right. So this claim is just saying that if you can solve point query with a slightly bigger k, instead of k, it's 3k, then you can use, and your failure probability has to be delta over n. You can use that in a black box way to solve the heavy hitters problem. Okay, so why does this query algorithm work, this for loop, and why am I doing 3k values? So, notice that if I is k frequent, so first of all, let's just condition on, how many times are we querying A? We're querying A n times, right? Because we have this for loop. And we're doing this query n times for each different I. I'm just going to condition on the event that none of those queries failed. They all succeeded. Now, each one fails with probability at most delta over n. So the probability that there exists one that failed is at most n times delta over n by the union bound. So, so that's delta. So the failure probability, the probability that any of these A dot queries failed is at most delta. And I'm going to show you that if none of them failed, if all of those queries gave me answers that satisfied the required error guarantee, then I'm going to show you that that's enough to argue that this for loop, that this whole A prime query algorithm succeeds, and L, L definitely has size at most O of K. That's guaranteed. It has at most size. It has size at most 3K. But you need to make sure that you satisfy the first definition, the first condition, which is that if an item is frequent, it needs to be guaranteed to be an L. And I'm going to show you that as long as all those queries succeeded, that will happen. So why is that true? So if I is K frequent, and we're conditioning on this event that none of the A queries failed, then what do I know? I know that xi tilde will be at least, well, I know that it's going to be at least xi minus 1 over 3k times the L1 norm. But xi itself is bigger than 1 over k times the L1 norm. That's what it means to be K frequent. So this is bigger than 1 over k times the L1 norm minus 1 over 3k times the L1 norm. So that's equal to 2/3, 2 over 3k times the L1 norm. Okay. So the key thing to note is just this thing, right? So I'm saying that if it's K frequent, xi tilde is strictly bigger than something. Meanwhile, if I is not even 3K frequent, then xi tilde will be at most xi plus 1 over 3k times the L1 norm, which is going to be at most 1 over 3k. Xi, if it's not even 3k frequent, that means xi is at most this. And that's the error, which is the same thing as above. Right? So again, so the key here is, look, and I should put absolute values here. If you're actually K frequent, you're gonna look big. You're gonna be over 2/3 blah. Whereas if you're not even 3K frequent, then you're gonna be at most blah. You're gonna be at most 2/3 blah. So you're gonna be less, strictly less. You're gonna be strictly less than all of the actual K frequent people. Okay. So basically, what this means is, if you can imagine, like, if I sort them, this is the top K people. This is the next top K. This is the next top K. So these are the top 3K people. And then there's a lot of people back here. All these people in this red region, okay, this is what this is saying in pictures. It's saying that if all the A dot queries succeeded, if you condition on the event, then all the people in the red region will appear strictly less than the people in the yellow region. Okay? So, what does that mean? That means that it is impossible that you have someone from the red region. No, I meant to make that red. It is impossible that someone from the red region made it into your list L, whereas someone from the yellow region didn't make it. Right? How could that be? L contains the largest 3K values. So the yellow guy is definitely larger than that red guy, right? That's what we just argued. So it's impossible that the yellow guy would be omitted, whereas the red guy would be inserted. So good. So this picture cannot happen, which means that if any of the people from the red region are included, it's because they're replacing someone in that white region, either the top 2K or let me, if I give it a different color, they're omitting someone in this region, right? Red people can replace those people, but they cannot replace yellow people. Okay. Does that make sense? So the top 3K items must have all the yellow people, because there aren't enough gray people to pad them out. They're at most, the number of people who are 3K frequent is at most 3k, which includes the k-frequent people, right? So that's it. That's the proof that, oh, you have a question?
I was thinking, yeah, that makes sense.
Okay. Any other questions? Okay. So these are very related problems. If I can solve point query, then I can solve heavy hitters. So let's see, how can I solve point query? So first of all, historically, there's an algorithm called the frequent algorithm that was invented by Mishra and Gries in 1982, I think. It solved, L1 point query and also heavy hitters deterministically. It was not a randomized algorithm, using at most 2k words of memory. In fact, it was at most 2k minus 1 words of memory. But this algorithm is insertion only. Okay. I will almost certainly put something related to this algorithm on the homework, which I'll release soon. I know you all have been dying to have some homework since we haven't had any yet. Is the OK space the space needed during the execution? Okay, so just to answer a question of everyone in the chat, again, please, if you have a question, just unmute yourself and ask it directly, because unfortunately the Linux version of Zoom does not give me pop-ups when there are questions. So I do not notice things in the chat. Actually, maybe I can fix that by leaving the chat up here. But yeah, so the OK spaces, I need to keep track of, as I'm doing the for loop, what are the top 3k items by frequency. So I'll just remember the top 3k items I've seen so far. Okay, so for the point query or heavy hitters problem in L1, the first algorithm was actually do the frequent algorithm. It was deterministic, but it did not work in the insertion. It did not work in the even strict turnstile model or the general turnstile model. It only worked in the insertion only model. But it is a very useful algorithm to know. It's an algorithm that is used in practice. So I'll make sure that you get practice with it on the homework. But I'm going to talk to you about the first algorithm for this problem that did work in the turnstile model. Or actually, it's the second algorithm, and then I'll go back to the first. So it does handle positive and negative deltas, and it's a linear sketching algorithm, and it's called the Countman sketch. And first, let me do it the strict turnstile one. Remember, strict turnstile means none of the entries in X ever go negative. So this is called the Countman sketch. And it's due to Kormod and Muthukrishnan. I want to say in 05. And this is the idea. The idea is what I'm going to store in memory is a grid of counters and the number of columns in this grid is going to be B, which is, some constant times K. And the number of rows is going to be, let's call it L, which is some constant times log whatever. Actually, in the strict turnstile model, it can basically just be log base 2 of 1 over delta, where delta is my desired failure probability. And I'm also going to have hash functions, one per row. So I have a hash function h1, which maps the universe into B. I have a hash function h2, which maps the universe into B, etc. And then someone comes along and says, update I delta, which remember means xi gets xi plus delta. So what do? I just hash I in each row. It sends it to a random column, and then I add delta there. So I'll apply h1 to I. I get a random entry in the first row. I'll add delta there. I'll apply h2 to I get another random column. I add delta there, etc. Okay. So I basically get L counters that get updated. Now, I would like to point out that, this is a linear sketching algorithm. Why is it a linear sketching algorithm? Because I could, what I'm storing in memory, right, is this grid of counters. So memory, and all these are from a 2-wise independent family, drawn independently from a 2-wise independent family. So memory is, let's say LB words plus the seeds to represent the HIs. And if you remember, a 2-wise independent hash function, to represent it only takes log n bits of memory. I have L of them, so this in total is O of L times log n bits, which is, O of L words. Okay, good. Why is this a linear sketch? Well, I can write the matrix pi as follows. Let's focus on column I. I'll just say that the number of rows here is m, which is L times b. And let's just do the following. So here I'm imagining that I have basically L blocks of rows. And in each block, I have a 1 in a single location, and the rest of that block is zeros. Does that make sense? So the claim is that this picture and the previous picture are exactly the same. So maybe let me be a little more. Let me make it a little more concrete, actually. So let's say that it looks like this: 0, 0, 1, 1, 0, 0, and then 0, 1, 0. So that means that B is 3. And then L here, let's make L be 4. So 0, 0, 1. So it looks something like this. So what I'm saying, and let's say this is I right here. So someone said update I delta. Okay. So if you look in the first block, this block right here, it says 0, 0, 1, which means the third entry gets updated, which means you add delta to the third entry. Here, the first entry got updated, so you add delta to the first entry. Here's the third entry, here's the second entry. Because again, remember that whenever, what does linear sketching mean? Like if someone says x gets x plus, xi gets xi plus delta, this is the same thing I already said as x gets x plus delta times ei, which implies that y becomes y plus delta times the ith column of the matrix pi, right? So that's exactly what this is. I guess what you can imagine is I'm taking those blocks, and at each one I'm rotating the block 90 degrees counterclockwise, and then I'm stacking them one on top of the other. That picture should look exactly like the picture of the grid of counters that I drew below. Okay. So this is a linear sketch. The matrix pi is implicitly defined by the hash functions, right? So I don't need to store this huge matrix pi explicitly in memory. I can just recover entries as I need it because of the hash functions, right? And I already said on the previous whiteboard that to store all the hash functions combined is only O of L words. So I'm storing this giant matrix using only O of L words, and L is like log 1 over delta. So this is what I mean by kind of implicit representation of these big sketching matrices. Okay, so how can I use this for point query in the strict turnstile model? So let's just look at one of these counters where I hash to. Let's say this one. What's in that counter? Well, every time I got updated, the corresponding delta got added there, right? So the sum of all those deltas that correspond to I is there. What is the sum of all those deltas? It's just xi, right? So that counter has xi, but it also has some noise, right? Because there are other people who also hash there possibly. And in the strict turnstile model, no one is negative. So all those people are just adding more non-negative noise. Okay. Already this tells me that this counter is going to be a possible overestimate of xi. It's not going to be an underestimate, right? Because all the noise that's getting added is non-negative. So more specifically, what's in this counter is xi plus the sum over all j not equal to I. Let me write this indicator random variable of the event that h4, let's just name these. So this is 1, 2, this is like row r, little r. The rth hash function collided on I and j, xj. Does that make sense? Okay. So this is what I'll call I'll call this counter C, counter C for counter. Rth row, which column? It's the hr of ith column is going to be equal to this. And for all r, it's going to look something like this. So it has what I want, plus it has some noise. So this is what I'll call the noise. And let me call the noise E. Now, what's the expectation of E? By linearity of expectation, it's the sum over all j not equal to I of xj times the expectation of that indicator variable. And this is just the probability that they collide, right? And this is where I use pairwise independence, two-wise independence of the hash function, because I'm looking only at two items at a time, right? Whether or not I and j collide depends only on where I and j got hashed to. It doesn't depend on anyone else. So I just need that when you look at two items at a time, their hash images look uniformly random. So that's two-wise independence. So what's the probability that these two things collide? This is equal to 1 over b. Okay. So this is equal to, this is less or equal to the L1 norm of x divided by b. Okay. So that the noise is like a 1 over b fraction of the L1 norm. Now by Markov, that means that the probability that the noise is bigger than twice that is less than a half. And by the way, I'll just now let me just set now b is equal to 2k. So this is just equal to L1 norm of x over k. So the probability that the error exceeds a 1 over k fraction of the L1 norm is less than a half. So now that I've said this, what do you think a good estimator is? If someone point queries I, what's something that makes sense to return? What should I return? Remember, this is just one of the counters for I. This is this one. There are L of them, right? So there are these L different ones. I want to somehow combine them or do something to these L different counters to get a good approximation to xi. Yeah, the min. Yeah, so as I've said in the chat, the min, right? And that's why it's called the count min sketch. I mean, you know that they're all overestimates. So what's the best overestimate to take? The one that has the least error. It's the smallest one, because even the smallest one is an overestimate, right? So you know that you're getting less error out of it. So when someone says query, I'm going to return the min over all r between 1 and L of that counter, CRHRI. And the probability, let's say, and this will give me some xi tilde. The probability that xi tilde minus xi, first of all, you know it's an overestimate. So the probability that xi tilde, let's say, is less than xi, you know that's 0. The probability that xi tilde is greater than xi plus 1 over k times the L1 norm is less than 1/2 to the Lth power, right? Because that's what we said over here. We said, right, for a fixed R, the probability that the error in the rth counter is too big is less than 1/2. So what's the probability that even the minimum counter has error that's too big? That means if the minimum counter is too big, that means all of them are too big. So for all of them to be too big, that, you know, since they're independent, the h's are chosen independently from each other. That happens with probability less than 1 over 2 to the Lth power, right? And this is at most delta, because remember we chose L to be log base 2 of 1 over delta ceiling. Okay. So that's it. So the total memory is O of k times log 1 over delta.
It's that 1 over k L1 norm matches up with that like 2e over b from before.
Yeah, because I set b. You know, I hadn't initially. I just said b is something. I hadn't actually told you what b was.
Ah.
But right over here, I set b to be 2k. Right.
Oh, cool. So
Okay. So and this implies what? Remember that reduction here said that if I can solve 3KL1, if I can solve the 3K point query problem with failure probability delta over n, then that implies that I solve heavy hitters. So if I want to solve heavy hitters, I need to set delta to be actually delta over n. So this implies O of k times log n over delta for heavy hitters. Words. Okay, so we've now seen the full details of one heavy hitter algorithm. Any questions about that?
We want it within 1 over k of the 1 times 1 norm of x, like plus minus.
Yeah, so in fact,
Or like, do we want it exactly at plus 1 over k 1 norm and minus 1 over k 1 norm?
So yeah, so the way I define heavy hitters is you're allowed to, you know, the way I defined point query was you're allowed to underestimate and you're allowed to overestimate, right? And as long as your additive error is at most 1 over k times the L1 norm in magnitude. So this is doing even better because this is never underestimating. This is giving me something such that xi tilde is guaranteed to always be at least the true xi. But then I know that it could be overestimated by as much as this. So this isn't, even though it looks like a J or something, this is xi tilde. So I'm getting something like this. Okay. Now, let me ask you a question. Let's say that I'm not in strict turnstile, but I'm in general turnstile, which means that entries of x can go negative. You know, does anyone see a simple fix to all of this to solve the general turnstile case? Actually, I can just leave this the way it is. Yeah. I mean, what here, you know, I mean, in a general turnstile case, let me just write a little bit. In general turnstile, what I care about is the magnitude of the difference. So I look at say CR HRI minus XI, and I look at the absolute value of that. This is equal to, this is at most, by triangle equal, at most the sum of J not equal to I of that indicator of collision of xj. So if I take expectations of this, again, by linear expectation, I get this, right? This is still equal to 1 over b. So this is still at most the L1 norm over b, right? So I'm still getting that. So, but what's the what's the difference in general turnstile? What do I have to change?
Because you took the min, which gives you a good, like a nice tight upper bound, but doesn't give you a good lower bound because one of them's like really,
Right.
or like
So,
easily go really low.
So in strict turnstile, I kind of had it for free that I'm not gonna underestimate by too much, because in fact I know I'm not gonna underestimate at all if I use the min estimator. But in general turnstile, the min is not such a great idea because I might wildly underestimate the value of xi, because some of these xi's are negative, and they can actually bring down the value of the counter below what xi was. So instead, what I'll do is, in general turnstile, the picture will look pretty much the same, except instead of this 2 here, I'll basically just make this a 3. So let's, instead of this 2 in the bottom right, I'll put a 3 here. And instead of a half here, I'll put a third. Okay, and then I'll set b to be 3k. Okay. And then now what does this say? This says that, I have these L counters. A third of the time, I have too much error. But 2/3 of the time, my error is bounded the way I want it to be. So like the strict majority, the vast majority of the time, I'm getting good error. Okay? So where have we seen, we've seen this kind of situation before. You have many estimators. You know that 2/3 of them in expectation work. Kind of what should you do?
Take the median.
Yeah, output the median, right? And how do you analyze it? Use the turnoff bound. You say, look, 2/3 of them work in expectation. For the median to not work, that means that less than 1/2 succeeded. I expect 2/3 to succeed, but only a half succeeded, which means, I deviated by my expectation by something like 2L over 3 minus L over 2, which is some constant times L. I guess it's like L over 6. I deviated from my expectation by L over 6. The probability of this happening is, exponentially small in L over 6. So if I pick L to be some large constant factor times log 1 over delta, I can make sure that this exponentially small thing in L is at most delta. Right? So basically now the only thing you change is you output the median. So this is the usual thing. We saw it, I think, even in lecture 1, where you plus and then you plus plus, right? For like the Morris counter, for example. So the plus plus is the median. This is the same exact trick. Okay, so that's all I want to say about kind of the vanilla countman sketch. I did want to bring up 2 things. One is, in practice, this counter, this reduction that I showed you, if I can solve point query, I can solve heavy hitters. It kind of sucks, right? Because I'm imagining that n is ginormous. N is all words that could possibly appear as search query terms to my search engine, right? And if you notice the reduction from heavy hitters to point query, yes, my memory is low, but my running time is not low at all, right? My running time, here's the reduction. This is my solution to heavy hitters using point query. What's the running time of this query? It's at least n, because I have a for loop of length n. Okay. So naturally, people who want to do these things in real life, they don't want to spend n time solving a heavy hitters query. They want to spend something like k time, because the return list only has O of k elements in it. Why am I spending n time to find these k elements? Imagine k is 10. I want to find the top 10 elements. I'm spending n time, which is the size of the universe, to find these 10 elements. I'd rather spend something that's proportional to 10 time, to k. So even the original Countman sketch paper realized this deficiency and had a solution, had an approach to get around it. And this is the so-called dyadic trick, which is to improve the heavy hitters query time. In the original paper, they showed how to apply it to strict turnstile. It turns out that with some sophistication, you can apply a similar thing in the general turnstile case, but I'm not going to talk about it today. It's a little complicated. But the idea here is I have my universe. Let me just draw a few more. And what I'm going to do is I'm going to build, conceptually, I'm going to imagine that there's a perfect binary tree built on top of this universe. Okay. And then so the number of levels here is like log n, right? Log n height tree. And then what I'm going to imagine doing is I'm going to instantiate a count min sketch at every level, or just some point query. It doesn't have to be count min, just some point query data structure. So let's call this count min sketch at level log n, count min sketch at level log n minus 1. All the way up here, there's count min sketch. I'm never actually going to use this one at level 0. And, at the bottom here, there's an n-dimensional vector that's being updated in a stream. Here, there's an n over 2-dimensional. Here's an n over 4-dimensional vector. Here, there's a 1-dimensional vector. So when I see an update I delta, let's say update 2 delta, at the bottom level of this tree, I'm just adding delta to x2. So that is getting fed. That is getting fed here. But I'm also imagining that kind of this update is affecting every level of the tree, where basically an internal node in this tree represents kind of the sum of all the leaves in its subtree. So for example, this node right here above the 1 and the 2, every update that happens to 1 or 2 also gets processed there. Okay, which means I'm adding delta here. I'm similarly adding delta here. I'm also adding delta here. So this thing is getting an update 1 delta, because from this level's point of view, the first, this is an n over 2-dimensional vector. The first dimension in this level is the thing that's getting updated. And similarly here, I'm updating 1 delta, etc. Just basically the leaf to root path. Okay. And now I'm in the strict turnstile model, right? Remember, I'm in the strict turnstile model. So what does that mean? So let's just call these things, this is vector x0, this is vector x1, all the way up to vector x log n. First of all, notice that kind of for all levels L, the L1 norm is the same. Right? This is because it's the strict turnstile model. There's no negative entries, there's no cancellations. And the other thing to notice is that if a leaf I is heavy, that implies that all of its ancestors are heavy, K heavy, in their levels. Right? Because again, since it's strict turnstile, the mass of this guy, if 2 is heavy, then that guy's value is at least the value of 2, and it might even be larger because 1 is also contributing to his value. Same thing with all the ancestors. They're only going to be heavier. In fact, the value at the root is the entire L1 norm. So he's very heavy. He's everything. Okay. So this motivates the following kind of query algorithm. So first of all, is it clear what the update algorithm is? The update algorithm is, if someone says update I delta, you'll process that at the bottommost count min sketch, but then you'll walk up the tree, walk the leaf to root path, and you'll make an update at each level as you walk up to the corresponding internal node, which is an ancestor of 2 at that level. Now, what's the query algorithm? The query algorithm is going to be some kind of breadth first search. So I'm going to start at the root level. And at every level, I'm going to keep track of which people at that level are heavy. Okay. And then, I'm going to query their children and then kind of recurse down to the children themselves that are heavy. So let's just run through an example of this to make this concrete. So initially, I'm just going to have my finger on this guy. This is the root. I know he's heavy. He's everything. He has 2 children. I'm going to point query each of them, okay? And I'm going to ask, if it's the L1 norm, again, I know what the L1 norm is exactly. The L1 norm is just, the L1 norm of the stream is just the sum of all updates I've ever seen, again, because it's strict turnstile. So I can just check, point query, is this person, all right, let me do it like this. Is this person greater than the L1 norm over K? Similarly, is this person greater than the L1 norm over K? It might be the case that, one is, 0 are, or both are. Let's say that only this guy's bigger. So what does that mean? That means because of this item, because this is true, oops. Because this is true, in the bottom, if this guy on the left, if this left child is not heavy, no one in his subtree could possibly be heavy, right? Because if anyone, once someone is heavy, all his ancestors are heavy. So if the higher guy is not heavy, none of his descendants can be heavy. So I can just basically cut out this entire subtree. I know that this entire subtree is worthless. Ignore it. And then now I just keep recursing down the tree. This guy has 2 children. I point query, and maybe both of them are big. So I continue on both. And then they have 2 children. And maybe 3 of those children are big, but the other one isn't. So I'll say this one is big, this one is big, and this one is big. This one isn't. So I can take his whole subtree and ignore it from now on. And then I just keep walking down until I get to the leaves, and then I return the leaves that are big according to point query. Now, let's condition on the event that none of these count min data structures fail. Remember, these are randomized data structures. Okay, let's condition on none of them failing. What's the maximum number of circled guys I can have on any given level? Let's look at some particular level R or L, little L. How many people can be heavy on level L? Yeah, forget even about conditioning. Just like question, how many people can be heavy on level L? Any takers?
Okay.
Yeah, K, right? Because if you focus on level L, at level L, there is this, roughly n over 2 to the L dimensional vector. Its L1 norm is the same as the L1 norm of X. So I'm asking how many people can be more than a 1 over K fraction of the L1 norm of X, which is the same as the L1 norm of that vector. It's less than K, right? We talked about this earlier. There can be fewer than K people who are K heavy. Which means I'm only keeping track of, at most, K people per level. I'm doing this for log n levels. So the number of point queries I make is at most K log n. I make at most K log n point queries. Okay. So basically I need to make sure that, CML has failure probability at most, let's say delta over K log n. That way I can union bound and basically say that everything is succeeding. So you can do this kind of argument to get, something like your space will be O of, okay, there are log n levels. Each one is a Countman sketch with failure probability delta over K log n. So the space for that is K times log of K log n over delta. Which, it's certainly, it's always at most, let's say K log squared n anyway. Say the failure probability you just want to be at most 1 over poly n. And then your update time is, again, you have log n levels to update. Each one takes you log of k log n over delta time. So again, this is O of log squared n for the same kind of failure probability. And the query time, this is where you really save. The query time is not going to be linear in n anymore. So again, you have log n levels. Each one, again, you have these k people at that level, but each one of those k people, you're querying 2 of their children. So you're doing something like 2k point queries. So let's say so again, that's k times the time to do a point query is log of k log n over delta, which is O of k log squared n. Right? So you're really saving a lot in your query time. Instead of being O tilde of n time, like n polylog n time, your query time is k polylog n time, which is a lot better. Okay. It turns out that this is suboptimal. So it is possible to get O of k log n space, just like the bad reduction. O of log n update time, and 3 k times polylog n query time. So this is something, it's called the expander sketch. This is due to Casper Green Larson, myself, Hui Nguyen, and Mikkel Thorup. And the idea here is, it's still a reduction. It's showing that you can use point query to solve heavy hitters, but it's just that the reduction, I mean, even this dyadic trick is a reduction at the end of the day, right? It's saying all of these Kalman sketches here are solving point query. So this is just a different reduction, showing that there's a different way to use point query to solve heavy hitters. And kind of what this work does is it gives an even more efficient way to use point query to solve heavy hitters, such that you don't suffer in your space or update time at all compared to the for loop solution. But you do by a constant factor, but your query time is much better. But I'm not going to cover the details of that. I only have 5 minutes left. So what I want to tell you about is 2 things. So 2 more items regarding heavy hitters. One is the so-called tail guarantee. And 2 is LP heavy hitters.
Bless you.
Thank you, for P not equal to 1. So let's do the tail guarantee first. So the way I defined point query and heavy hitters, I said for point query, you should return xi plus or minus 1 over k times the L1 norm. The tail version, the tail point query says you should return xi plus or minus 1 over k times x tail k L1 norm. What is x tail k? X tail k is take the vector x, but zero out the top k entries in magnitude. Right. So the only thing that's left are the bottom n minus k entries in magnitude. So the L1 norm is only going to be smaller, right? It's not going to be bigger because you zeroed out a bunch of entries. So this is saying that your error should be even better. Instead of your error depending on the L1 norm of all of x, it should only depend on the L1 norm of the tail of x. And then again, for heavy hitters, you said to be heavy, we said that xi should be bigger than a 1 over k fraction of the L1 norm. But for tail heavy hitters, I'll say an item is a heavy hitter if xi is bigger than a 1 over k fraction of the L1 norm of the tail. Now, how many tail heavy hitters can there be? We already said that normal heavy hitters, there can be at most k minus 1. Tail heavy hitters, I claim that there can be at most 2k minus 1. Why? Because either I is in the head. Okay, if it's in the head, maybe it's bigger than a 1 over k fraction of the tail. I have no idea. But there are only k people in the head. Otherwise, if I is in the tail, that is basically the same argument as before. You're in the tail, but you're bigger than a 1 over k fraction of the tail. There have to be fewer than k such people. So the number of tail heavy hitters is basically at most k, this is the head, plus k minus 1, this is in the tail. So this is at most 2k minus 1. So you could ask, can I solve the tail version? Can I solve of point query? Can I solve the tail version of heavy hitters? And the answer is yes. And basically, using the count sketch, you don't have to change the algorithm. Just a different but similar analysis of the same exact algorithm works. And I'll just give you a flavor of it. So let's look at again the count min sketch in the strict turnstile model. We said that CR HR of I is equal to xi plus the sum of j not equal to I of the indicator of collision of xj. Let me write this as xi plus the sum over j not equal to I, but j is in the head of that thing, plus the sum of j not equal to I, but j is in the tail of the same thing. Okay. Now, how many people are in the head? K. How many buckets do we have at this level, at this row? We have B buckets. Think of B now as being like 10K. Okay. So they're only K head items, but they're getting hashed into 10K buckets. How many of those 10K, like other than I, how many of those 10K people do we expect to land in I's bucket? Right? We expect a 1 over bth fraction of them. There are only K of them, so that's like K over 10b. We expect K over B. So we expect at most K over B to collide with I. But if B is 10K, that means that the number we expect to collide with I is a tenth. It's less than 1. So an expectation, less than 1 person is colliding with I. And more specifically, by Markov's inequality, the probability that we have even 1 collision with I, that means, well, to have 1 collision, when I only expect 1 over 10 collisions, that means I exceeded my expectation by a factor of 10. By Markov's inequality, that happens with probability at most a tenth, right? So with probability 9/10, this part is 0. Right, by Markov. And then you just do the previous argument on this part. This part has expectation equal to, or at most, 1 over b times the L1 over the tail. Right? And then you do the Markov on that, and you return the min, and it's just like before. So the analysis doesn't actually have to change by much. The second thing that I want to talk about is LP for p not equal to 1. So again, I'll just wrap this up in the last 30 seconds. So disjointness, there's a reduction from disjointness, which implies that LP heavy hitters for p bigger than 2 requires polynomial space. Another thing that you can prove is that if p is bigger than q, that implies that 1 over 2k, so I'll justify this, I'll say what I'm doing in a second, 1 over p times x tail kp is at most 1 over k to the 1 over q x tail, and let's call this 2k. Okay. remember, like what is, sorry, so, and also LP point query says basically return xi plus or minus 1 over k to the 1 over p times x tail p. I'll probably give you some practice with some of the homework. Right. So remember, this part here is your error term in point query, right? And what this is saying over here is if a larger p norm, like for example, p is 2 and q is 1. Let's say, for example, p is 2 and q is 1. The error term from the LP version is at most the error term from the LQ version. But you might need to adjust k by a factor of 2 to make that true. But if you adjust k by a factor of 2, then it's certainly at most, it's at most the right-hand side. The left-hand side is at most the right-hand side. So what this is saying is the kind of error guarantees, and by the way, I mean, it's not just less than or equal to, I mean, you can construct examples where it's like very, very much less than. The left-hand side is just way less than the right-hand side. So kind of what this is saying is I basically would like to ideally solve, if you tell me, hey, do you want to solve k point query? Let's say k is 10. I fix k. Do you want to solve k point query for L1 or L2? Which one do you prefer? And, all things equal, if they're both using the same memory, I would prefer to have one that solves the L2 version. Because what this thing is telling me is that the L2 version's error is at most the L1 version's error, up to changing k by a factor of 2. So it's better, it's less error, right? So the first bullet says, I can't hope to solve the problem when p is bigger than 2. The second bullet says, the larger the p, the better, the better meaning lower error. So let me try to make p as big as possible. Oh, I can't make p bigger than 2 because that would require a lot of memory. So the best I can hope to do in low memory is to solve the case that p equals 2. And in fact, there's something called the count sketch. This is due to Charikar, Chen, and Farage-Colton. That solves the L2 version of point query as well as any other. And it uses O of like k log n memory. Okay, so that's all I have for you today. I'm over time. Let me end the recording. Are there any questions?